Hi, my name is Rowan Border, and I am a researcher with Jonathan Gamel's Estimation Search and Planning Group in the Oxford Robotics Institute at the University of Oxford. This video presents our work on the proactive estimation of occlusions and scene coverage for planning next best views in an unstructured representation. The ability to capture 3D observations of the real world is valuable for the inspection and simulation of scenes varying in size from small-scale objects to large-scale buildings. These observations are typically obtained by capturing point-based measurements of a scene from multiple viewpoints using a 3D sensor, such as a LiDAR or a depth camera. The viewpoints from which sensor measurements are obtained are typically chosen by considering a priori knowledge of the scene structure and measurement information obtained from previous views. The challenge of identifying which view of a scene to capture next in order to obtain the best improvement in its observation is known as the next best view planning problem. The information obtained from sensor measurements is encoded in a scene representation. Most approaches use structured representations. These encode scene information within an explicit framework, such as a voxel grid for volumetric representations or a connected mesh for surface representations. Volumetric representations with a voxel grid are the most common. While these structures can simplify the planning problem, they often limit the fidelity of scene information expressed and can be expensive to maintain. In contrast, unstructured scene representations only utilize the intrinsic point measurements obtained without imposing an external structure. The Surface Edge Explorer, known as C, is the next best view planning approach that uses a novel unstructured density representation. This representation classifies every point measurement based on the density of neighboring points as either a core, frontier, or outlier point. Core points represent fully observed scene surfaces, outlier points denote partially observed surfaces, and frontier points lie on the boundary between the two. A view is proposed to observe each frontier point and expand the boundary of fully observed surfaces. Next best views are selected until there are no remaining frontier points and the scene has been fully observed. They are chosen to reduce the travel distance from the current sensor position. Our work on C was presented in a conference paper at ICRA 2018. C was compared experimentally with approaches using a volumetric representation for the observation of 3D models in a simulation environment. It was shown to obtain greater scene coverage while using less computational time. C was also able to observe the scenes using fewer views, but often traveled farther to do so. This inefficiency can be attributed to the use of reactive view adjustments to avoid occlusions when a frontier point cannot be observed from its proposed view. While this strategy is often successful at observing frontier points, it typically requires multiple views and an increased travel distance. The method for choosing next best views also exhibits inefficiency, as the improvement in scene coverage attainable from each view is not quantified and considered in the view selection process. In this work, we present novel techniques to address these inefficiencies in C. This work presents a more efficient strategy for handling occlusions, which proactively detects and avoids them before obtaining a view. This mitigates the need to apply incremental view adjustments when the presence of an occluding surface is already known, and increases the likelihood that a frontier point will be successfully observed from its first view. In this representation, occlusions are denoted by the presence of occluding points between a frontier point and its associated view. They are detected by performing incremental radius searches along the sight line from the frontier point to its view, up to a user-specified distance psi. The view is considered occluded if any points are found within a radius search. When the view proposed to observe a frontier point is found to be occluded, an optimization method is used to identify an alternative, unoccluded view. This view is chosen to maximize the separation between its sightline to the frontier and any occluding points. It is found by solving a maxi-min optimization problem. Occluding points within a user-specified radius of the frontier are projected onto the surface of a sphere centered on the frontier point. This normalizes their distance while preserving their orientation relative to the frontier. The maxi-min optimization then computes a locally optimal point, phi star, on the sphere surface, which maximizes the minimum distance to any of the projected points. This optimal point defines the sightline of an unoccluded view. When selecting a next best view, it is desirable to obtain the greatest improvement in a scene observation while incurring the least cost. In the context of this work, the improvement in an observation is quantified by an increase in surface coverage, and the cost of obtaining a view is measured by the distance travelled. The view selection method used by C aims to reduce the view cost, but does not consider the increase in surface coverage attainable from each view. This can be quantified by determining the number of frontier points visible from each view. The visibility of a frontier point from a view is evaluated using the occlusion detection method. Every frontier point is associated with the view proposed to observe it, and they can be represented together as a frontier view pair. If a frontier point, Fi, is visible from the view associated with another frontier, Fj, then the frontier view pair Mi is said to be co-visible from the frontier view pair Mj. These co-visibility relationships can be bidirectional or unidirectional. The co-visibility between frontier view pairs is encoded in a frontier visibility graph. In this graph, the vertices represent frontier view pairs and the directed edges denote co-visibility relationships. A next best view, Mi+1, is selected from this graph to observe the most frontier points while moving the least travel distance to do so. This is achieved by identifying the vertex with the greatest number of outgoing edges that can also observe the frontier point associated with the pair MC, whose view is closest to the current sensor position, Xi. The performance of the presented strategies for proactively handling occlusions and considering scene coverage is evaluated by extending C to create C++. An improvement in the efficiency of frontier observations is demonstrated by a statistical analysis of the number of views and travel distance required to observe each frontier point. This analysis is computed from simulation experiments on 4 standard models from the Stanford 3D repository. The results show that C++ is 4.5 times more likely to observe a frontier point with a single view than C, and 11% more likely to observe one while traveling less than 3 meters. The improvements in frontier observation efficiency achieved by C++ enable it to obtain complete scene observations while using fewer views and shorter travel distances than both C and approaches that use a volumetric representation. While this improved efficiency incurs an increase in computation time per view, C++ is still able to observe scenes using significantly less computation time than the volumetric approaches. In some cases, the improved observation efficiency of C++ is also sufficient to observe scenes with less computation time than C. This video shows a time-synchronized comparison of simulation experiments run with C, C++, and 2 volumetric approaches. A small-scale 1-meter model of the Stanford bunny is being observed using a simulated depth sensor. The results show that both C and C++ are able to plan views using less computational time than the volumetric approaches. C++ demonstrates its improved observation efficiency by leveraging an increased computation time per view to observe the scene in this experiment using 38% fewer views and a 43% shorter travel distance than C. This video shows another time-synchronized comparison of simulation experiments run with C, C++, and 2 volumetric approaches. In these experiments, a full-scale 40-meter model of the Radcliffe Camera Building in Oxford is being observed using a simulated LiDAR sensor. These results show that the computational efficiency of the unstructured scene representation used by C and C++ scales effectively to the observation of larger scenes. C++ also retains its improved observation efficiency over C, as it is able to observe the scene in this experiment using 43% fewer views and an 11% shorter travel distance. This video shows the result of a real-world observation obtained using C++. The skull of a saltwater crocodile was observed with an Intel RealSense D435 depth camera. The camera was attached to a handheld sensor wand whose pose was tracked in a known global frame using a Vicon motion capture system. Sensor measurements were captured using the RealSense and processed by C++ to propose a next best view in the Vicon coordinate frame. The sensor wand was then moved by hand to the proposed view and new measurements were captured. The raw point cloud obtained from the observation was post-processed to generate a colored surface mesh shown in the video. This shows that C++ was able to successfully obtain a largely complete observation of the crocodile skull despite the complex occlusions in its structure and the presence of significant sensor noise. In summary, this work presents novel techniques to address inefficiencies in the view-proposal and selection methods used by C. Occlusion handling is improved by addressing known occlusions proactively rather than applying reactive view adjustments. Unoccluded views are then proposed to avoid known occlusions. The new approach to view selection increases the surface coverage obtained from views by considering the shared visibility of frontier points. The resulting C++ can obtain complete scene observations using fewer views and shorter travel distances than C and the volumetric approaches while retaining a low computational cost. This observation ability is also demonstrated on a real-world scene. Information on the open source availability of C++ can be found at robotic-esp.com/code/C. Thank you for listening to this presentation. For more details on this work, please read our IROS 2020 paper.